Hi, let's take a look at our example of B plus tree operations. We're going to be inserting records with specific key values into our file, which is being indexed by a B plus tree. We're going to consider these keys being inserted in this particular sequence. So we start off with Diane. We're inserting this into a B plus tree of order 3. And the implications of that are the following. For an internal node, a minimum of 2 pointers, a maximum of 3 pointers. So a very simple structure. If we, because of splits, need to insert a fourth, it's going to cause a split in an internal node. A leaf node will have at least 2 key pointer pairs, a maximum of 3 key pointer pairs. Inserting a fourth key will cause a split. So this is strictly for example purposes. Typically, P would be very, very large. When we insert a record with the key Diane, the index is going to have just a leaf node with the key Diane, a reference to a component, a data component, where a record with that key value can be found. So it might be a pointer to an actual block, or to an actual record. And here is just an indication that we only have the one leaf node, and so the horizontal pointer here is null. When we insert Corey, Corey belongs in this leaf node, of course, and these keys are kept in ascending key sequence, so Corey precedes Diane. Next, we insert Raymond. Raymond fits here. We've now reached our maximum capacity. Corey, Diane, Raymond in this particular sequence, ascending key sequence. Inserting Amy, logically speaking, belongs in this way. Amy, Corey, Diane, Raymond in key sequence, but we don't have capacity for this. It has to split. It's a 50-50 split. Amy and Corey will stay here. Diane and Raymond will be moved off into a newly allocated node. Now we'll have 2 nodes, 2 leaf nodes, which will be chained together. And so this node with Amy Corey has a pointer, a reference to this node with Diane and Raymond. Here we have 2 nodes. For the leftmost leaf has Amy and Corey, the rightmost has Diane and Raymond. They're chained together horizontally. They need a level above them to index them. And so what happens is that this key value Corey, the largest in the left, goes into a newly allocated root node, along with pointers to these 2 leaf nodes. And so when we go to the next slide, we see that this happened here. And we have a proper ordering of this tree. Looking at the root node, the left pointer is pointing to a subtree that contains key values less than or equal to Corey. The right pointer is pointing to a subtree that has key values strictly greater than Corey. Let's go back to slide, or go up to slide 21. Internal node splitting, but it's not the root. On the next slide, we have when a new root is formed, which is just the situation that has happened, a key value and 2 pointers must be placed into it. And so the key value is Corey, and the pointers are to the 2 leaf nodes. Corey has a reference to the left sibling and a reference to the right sibling. Let's carry on. The next key value to be inserted is Miranda. A search of this tree tells us that Miranda, a search starting at the root, Miranda is greater than Corey, so we go to this particular subtree, which is now a leaf node, and so Miranda belongs here. It should be Diane, followed by Miranda, followed by Raymond. And so that's the situation we have. And next, Marcia was inserted. Now, search of this tree, starting at the root, Marshall is greater than Corey, And so we follow this to the subtree here, but that is a leaf node. This is where Marshall belongs. It should be Diane, then Marshall, Miranda, Raymond. And so a 50-50 split must be done. Diane and Marshall belong in this node. Miranda and Raymond go into a newly allocated node. And then the high key value in the left sibling is promoted to or copied to the parent. And we'll end up with Corey and Marshall being up here. And that's what we see depicted down here. So here we have Amy, Corey, Diane, Marshall, Miranda, Raymond, all chained horizontally in ascending key sequence. Up above, we have included Marshall as a discriminator. And to the left of Marshall, we have this reference to the original leaf node that's split. And a reference to that new one is the pointer just to the right of Marshall. And again, we have a well-ordered B+ tree. The next insertion is for Zena. Zena, a search of the tree tells us it belongs in this particular node. Searching the root for the first key value greater than or equal to Zena. Well, it's not Corey, it's not Marshall. There isn't such a value, and so we follow the rightmost pointer to this subtree. Zena belongs here after Raymond. And so this is what that leaf node looks like when Zena is inserted. The next insertion is for Rhonda. Searching this tree, starting at the root, Rhonda is not less than or equal to Corey, not less than or equal to Marshall. And so again, we follow this pointer to the rightmost subtree, which is a leaf. And so Rhonda belongs here, logically speaking, between Raymond and Zena. But this node is overflowing. It needs to split into two. The leftmost or the lesser key values are kept in this node. The higher key values, Rhonda and Zena, go into the newly allocated node. And then Raymond, along with a reference to that newly allocated node, is promoted to the parent. So logically speaking, this is what we end up with. Our leaf nodes, the rightmost one being Rhonda and Zena. And logically speaking, we need Raymond here as a discriminator between these two subtrees. But this is exceeding the capacity of an internal node. And so again, we have a root, which is going to be splitting. And what's going to happen is that Marshall has to be moved into a newly allocated root node, along with a reference to this internal node, and a reference to a newly allocated internal node, which contains Raymond. And so what we end up with is this. Corey stayed in that internal node. Raymond is in a newly allocated node, and Marshall was promoted to the new root, along with two references, one to the node with Corey, one to the node with Raymond, and we still end up with a well-ordered B+ tree. If you look at this pointer to the left of Marshall, that's pointing to a subtree where all the key values are less than or equal to Marshall. And the right pointer is pointing to a subtree where all the key values are strictly greater than Marshall. When we look at the insertion of Vincent, well, Vincent is greater than Marshall, so we follow this subtree. Vincent is greater than Raymond, so we follow to this subtree, which is a leaf node, and so Vincent belongs here between Rhonda and Zena. Vincent fits, and we carry on. But now we consider the insertion of Simon. The search tells us that Simon belongs in that leaf node, but let's go through it. Simon is greater than Marshall, so we follow to this subtree. Simon is greater than Raymond, so we go to this subtree, which is a leaf. And so Simon belongs here between Rhonda and Vincent. And what happens is that we're exceeding the capacity, and so it needs to split. Rhonda and Simon, being the lesser values, stay here. Vincent and Zena, being the larger values, go into a newly allocated node. And then that high key value of the original node, so that node contains Rhonda and Simon. Simon is copied to the parent along with a pointer to that newly allocated node. So this internal node up here with Raymond is now going to have Raymond and Simon. Let's take a look. And here we have Raymond and Simon and this reference to a newly allocated node containing Vincent and Zena. The last one to be inserted is Mary. And it was determined that Mary belongs in this particular node. A search of the B+ tree tells us that this is where Mary belongs. Let's look at that process. We start at the root. Mary is not less than or equal to Marshall. Mary is greater than Marshall, so we follow to this subtree. And then our search algorithm would scan these keys looking for the first one greater than or equal to Mary, which is Raymond. And so following this pointer, we get to this leaf node. That's where Mary belongs. And Mary belongs in this node just before Miranda. And that takes us to the end of that example. We'll ask you to do something similar in our last assignment. Let's just review some things about B+ tree operations. We're only concerned with search, retrieval, and insert. Search, we say the search is always the same cost. You're starting at the root, being a balanced tree, reaching a leaf node is always the same cost, which is the height of the tree. We say the cost of finding a record is going to be the tree height plus 1, because we need to get to the data component in order to get to the record. With respect to retrieval, if you need to access rows or keys in ascending key sequence, the B+ tree facilitates that. So if you were looking for, or say you had an SQL statement, select asterisk from employee where ID is greater than 50. The system would search through the B+ tree to find the leaf node relevant to 50. And then it just needs to follow the horizontal pointers in order to access successive rows, successive records. So sequential access by that particular key value is facilitated. You just need to go through the index once and then follow the leaf nodes. Insert requires a search of the tree to find out where a record belongs. And usually, because the order of the B tree will be very large, there's just one operation to update a particular leaf node. Occasionally, an overflow will occur, and so that leaf node would need to split into 2. And there may be some management of index nodes above that. There may be changes all the way up the tree, in which case the tree would grow in height. We're not concerned with delete in 3902, but if you have an interest, do take a look at that in our textbook. Thank you. Bye-bye.